Thanks so much for the introduction. It's good to be here. It's here a number of years ago. Beautiful place in the winter, and now it's a bit warmer. Okay, so today is I'll talk about a sequence of works. Sequence of works with archive numbers here, and a most recent paper at the end on in which the last part of the title on the pion amplitudes, a certain construction of pion amplitudes at the very end, NLSM. Okay. So what in quantum field theory, amplitudes usually live in momentum space, and there's a construction of them due to Feynman, which says that you can express them combinatorially by summing over graphs living on momentum space, but often these expressions are ultimately much simpler, like we learned from Park and Taylor, and so that sort of begot the positive geometry program, in which case amplitudes were considered to be volumes of certain objects, like ultimately the Amplituhedron, which is maybe the first example of what was eventually positive geometry. So the question that I ask now is, what if amplitudes knew about more general geometries? Okay, so what if Feynman? So two ideas. What if the Feynman diagram prescription, this we know, is representable as a volume, and more generally, what if instead of a formulation, which I'll explain, the amplitudes are volumes of configuration spaces, not in P1, but in pk minus 1, right? So they're going to be sort of higher dimensional objects, and this is what we're going to consider today. Right, so what are we seeing? We're seeing novel factorization patterns in this new theory. Particles can split in sort of new and interesting ways instead of the usual prescription, where you have a Feynman diagram and you have a particle's momentum passing along the internal legs, and you just do a cut, and it splits into two pieces. Okay, I'm introducing a new object, in which case you can split into more pieces at just an initial residue. Okay? In the construction, the notion of Feynman diagrams is replaced by tropical geometry. In particular, instead of a single Feynman diagram, you're going to have a cone in space, and these cones will sort of tile, and your amplitude will be a sum over all of the cones as they tile your space. Okay, so today I want to talk about going from the simplest quantum field theory, planar phi cubed, which consists of cubic interactions, to more interesting actual physical theories, the nonlinear sigma model, and then Yang-Mills. And then I'll explain how these theories also extend into moduli spaces of points in pk minus 1. Okay, so just some history. So positive geometry roughly began around the time of the Amplituhedron, the introduction of the Amplituhedron, and then it was written up in, I think, 2017 or so. And in the story I'm describing, it sort of begins in 2019 with a formalism called scattering equations. The scattering equations formulate scattering amplitudes as certain integrals over a configuration space. Okay? In 2019, so this configuration space was extended from n ordered points on the projective line into n moduli space of polygons in the projective plane, and so on. So in that way, we realized that instead of Feynman diagrams, we can replace them with these exotic objects called tropical Grassmannians, and then we got just sort of the full geometric combinatorics program just kicked in, and we saw things like matroid subdivisions, residual embeddings, minimal kinematics, and as we're going on towards 2025, then there was a connection to so-called quantum affine algebras and the dual canonical basis. So John Wrong in the audience will answer questions about dual canonical bases, but roughly the idea is that they sort of refine this configuration space structure. And finally, at the very end, just earlier this year, we have the construction of the nonlinear sigma model in this generalized story. Okay, so structural, we have positive geometry at we have positive geometry at the beginning, and positive geometry, well, I should, since this is a positive geometry workshop, let me remind, positive geometry is a semi-algebraic set equipped with a pair consisting of a semi-algebraic set and a complex variety and a logarithmic differential form, which is iterative. It's recursive, such that on every residue of this semi-algebraic set, you take a residue of that canonical form and you get a new positive geometry on the boundary. Okay, well, these are some of the pieces. In this generalized story, what we see is that quantum field theory actually lives on the boundaries of these amplitudes. They live on residues. And here's what it looks like. Schematically, we have the object in the middle is the new amplitude, and on one of the faces we have the usual trace phi cubed or planar the planar cubic scalar theory. And that's in the sense that it is backwards compatible. That if we take this amplitude, rational function, defined on a configuration space, take some residue, and we get, on that boundary, we get an actual copy of the standard physical theory. And here's what it actually looks like. It reflects this recursive structure. So on the, if you look here, M2n, M27, M26 live on the boundaries. We sort of have these generalized theories living in the interior. And the arrows correspond to taking certain residues. So we start anywhere in the middle, take some residues, and we end up with the cubic scalar theory on the boundary. Okay. Right, so, okay, well, how did we arrive at this?
Do you mind going back to the picture, if that's okay?
Sure.
So how do you actually understand this trace phi cubes in the bulk of the associahedron and the
Yes.
related to CEGM?
Yes. So this is schematic. The associahedron is a different higher dimensional polytope, and it starts at dimension 4. Okay, so this polytope is related to the positive tropical Grassmannian. Right, so.
Dual.
What's that?
Dual to it.
Yes. It's related to the positive tropical Grassmannian, yes. Mm-hmm.
So, Nick, sorry, are you saying the sketch you drawn on the right hand side, is it a facet of a 4-dimensional polytope?
Actually, that is what it is, yes. Right. Yes, trace phi cube at n equals 6 points. M36, you take one residue and you get a 3-dimensional facet. Yeah, and so on. Mm-hmm. Thanks. Okay, so planar kinematics. If you take an amplitude, take the cubic scalar amplitude, it has some number of Feynman diagrams and it is in its expansion. And they are functions of they're functions on the momentum space, and it has exactly Catalan many Feynman diagrams. And if you specialize each of those to 1, what happens is that you actually just count the Feynman diagrams. Okay, so this is what this is construction. It led to this formula, which is if you take take a 5-point interaction in the cubic scalar theory, the 5-point color-ordered interaction, and that consists of 5 cubic trees. Well, you can rewrite that as a sum over 5 two-dimensional cones, and you write that as some piecewise exponential integral. And so on each cone, what you get is it's linear on each maximal cone, and you get a different Feynman diagram. All right, so the main story is, the punchline is that planar kinematics, by taking these restrictions, they actually suggested how to arrive at this global Schwinger parameterization. And so that was kind of the start of the story. Okay, so yeah, that's the start of the story. Yeah. So we also looked at these so-called, if you take the cubic scalar theory and you take a planar order, a planar equals cubic order, which means that Feynman diagrams are in a disk, okay, and you consider all cubic trees embedded in that disk. Well, that is inherited from a color structure on the amplitude. And in the generalization, we had to find what is the notion of color, and that was kind of a challenge, and that led to the study of more combinatorics, even more combinatorics, using real hyperplane arrangements and oriented matroids. Okay, so we have that led to the introduction of new objects beyond the positive Grassmannian. New objects beyond the positive Grassmannian that computed these objects, these amplitudes. Okay, I think we're reaching the end of the sort of introduction. So sort of to summarize, to give some open questions here, we saw that on the boundary of this four-dimensional polytope lives the isosahedron. Okay, lives phi cubed. We saw that tropical geometry formulates the cubic scalar theory as a single piecewise exponential integral. We saw that there is a distinguished, we will see in a moment the definition, that there is a distinguished basis of propagators for the color order, the planar cubic scalar theory. In the generalization, we see some novel factorization patterns, and the open questions we have are extending this in various directions to string integrals. Okay, so so the planar basis framework. So a bit of combinatorics. We're going to replace Mandel-Stem invariance, Sij. Replace Mandel-Stem invariance with a new set of propagators, denoted by k-element subsets. Xj is a k-element subset. We're going to encode the standard construction of Feynman diagrams in terms of a polytope. This polytope is called the hypersimplex. It's given by the convex hull of a lot of 0, 1 vectors. But if we want to construct the propagators, we want to construct the propagators for the color-ordered cubic scalar theory. Well, we need a formula, and in this generalization, it's not so obvious what to do. This formula is what does it. You have to take a walk on the one skeleton of this hypersimplex, and the length of that walk gives you the coefficient of the Feynman diagram. And what's going to happen is there's a miracle here, which is that modulo momentum conservation this reduces to a standard propagator. Right, so for example, if we go here, this formula reduces x24 here, reduces modulo momentum conservation to S12, minus one invariant, x13 becomes S23, and so on, right? And so when we take cyclically adjacent indices, that encodes momentum conservation.
Sorry, Nick, how are the x's defined?
The x's are defined using, in the k equals 2 case, there are these simple summations. And in this generalized case, which coincides when k equals 2, it's this formula here. I'll stay here for a minute.
Okay. All right. Thanks.
Yeah. So this is a really remarkable formula from a combinatorial point of view, and also from a physical point of view, I think. Right. So again, we have a walk in the directions of these vectors: E1 minus E2, E2 minus E3, En minus E1. Okay, and we fix two vertices in space, and we compute the distance, the minimum distance from vertex 1 to vertex 2 in those directions, in those step directions. And that gives us the coefficient of the Mandel-Stem invariant S12. Okay? We walk from x13, walk from E13 to E34, and we get a coefficient 1, because it's one step. E1 minus E3, E1 plus E3 to E1 minus E4 is just one step. And so on. And so we take our walk around our object, and we get this new expression for the x's.
What happens for k equals 1?
Oh, there is no k equals 1. It's completely trivial.
You did include it in your formula, that's why I was wondering.
Yeah, right. No, good, great, thank you. So when k equals 1, the analog of momentum conservation would just destroy everything. So there's a zero-dimensional kinematic space.
Nick, how do you calculate this distance? Like, is there a nice combinatorial algorithm to calculate this distance?
Oh, yes. There's a simple linear function. It's maybe I won't write it down, but it is a min of n vectors.
Okay, all right. I'll ask you.
Yeah.
And what is momentum conservation in this?
Momentum conservation.
Okay.
For general k, you set any consecutive interval to 0.
Okay.
X sub any consecutive interval to 0 gives you momentum conservation. Okay. Right. So this directed distance formula. In the case n equals 2, there's a two-dimensional kinematic space is two-dimensional. There are two planar kinematic invariants. And there they are given. Right, and so these have the property that these are both poles of the amplitude. Right, the cubic scalar amplitude is 1 over x13 plus 1 over x24, and that gives you sort of a basis of linearly independent objects. Okay.
I thought S12 is a pole of the amplitude if you just think of the Feynman diagrams.
Yes.
But then you say x24 is a complicated polynomial.
Yes, but it reduces, it reduces to S12 on the left-hand side.
By momentum conservation.
By momentum conservation, yeah.
You prefer to write them in this way for some reason.
Because that's the only way I know how to prove certain things, to construct certain things and prove certain things in this generalization. Yeah. So proving linear independence for these xij's is easy from this formula, but yeah, so it's not so obvious in general. Yeah, so here's what I was saying in words. For the color-ordered phi cube theory, there is our amplitude. It's the sum over the two triangulations of a foregone. And for a five-gon, we have the sum over the triangulations. Okay? So if we drew a five-gon, we'd have 1, 4, and 2, 4. Form the two chords in the triangulation, and you sort of take a cyclic orbit of that. Okay? And these x's, xij's, are in bijection with the normal vectors to the associated. Okay. When you have a Feynman diagram, and when you have, let me go back. When you have a Feynman diagram and you have a collection of S's or a collection of xij's, you want to know when do they appear in that same expression. When do they appear in the same Feynman diagram? And that's exactly when you have non-intersecting chords in the triangulation of the polygon. Well, it turns out that the general story, and in particular for k equals 2, is encoded into the so-called positive tropical Grassmannian. I want to give just give the definition here. Pi is a vector in R to the n choose 2 when k equals 2. Okay, it's a vector in that space. You take it is a vector which is actually dual to the planar kinematic invariant. And it's defined by these three-term positive tropical Plücke relations. Okay. So the construction of compatibility, when we want to take two chords, I'm going to say when are two chords intersecting or not. That construction is phrased as if you take you take two chords and take the difference of the vectors, and ask how many times does that alternate in sign. Sorry, have some chalk here. Right. Can I put this up for a second? Yeah. So we take E1 plus E3 minus E2 plus E4, and that's equal to 1, negative 1, 1, negative 1, so the two diagonals of a square. So you count the number of sign changes, and it alternates sign 4 times. So that's, from this perspective, that's why they're incompatible. Okay. All right, so the fact is, if we have one of these x's given by our formula, remember our formula in terms of the directed distance function, we ask, when does xi and xj appear in the same Feynman diagram? We have to ask, when does xi plus xj satisfy these relations? That is, when do the coefficients of xi and xj satisfy these particular relations? And so that condition is equivalent to, the theorem is that condition is equivalent to taking the difference of these vertices and counting the number of sign changes, right? So, so geometric picture is, yeah, you have two vectors in space, you take the difference. It's the vector connecting the two of them. Two vertices of the hypersimplex. Okay?
You have some similar kind of intuition. For k equal to 2, you have this chords in an n-gon which intersect or do not intersect. I mean, if I take k equal to 3, is there some picture in 3 dimensions where this compatibility can be understood as something about triangles? Or
yes, exactly. So what actually happens is this notion of compatibility, it reduces exactly to the k equals 2 case on if you go to a high enough boundary of the hypersimplex. So the statement is, we take two vertices of a k equals 3 hypersimplex, and you can find a k equals 2 type violation on the boundary. You can find a pair of crossing chords on the boundary.
Is this necessary and sufficient for k equals 3 incompatibility?
Yes.
Nick, are you going to tell us about the picture of these as lattice paths? Because, I mean, that's also like a nice way.
Yeah, exactly. No, I didn't want to do that today. But
Okay.
yeah, many different ways to look at the same object. Yes, these are they're related to Schubert matroids, nested matroids, lattice path matroids, and so on. Yes.
Sorry, just to follow up on the question. So for xij, I usually would think of chords in an n1, right? 2D. Everything is in a plane. So could I think of these x sub I as like a hyperplane, and then this is like k-dimensional simplex?
Awesome. Thank you very much. Yes, great question. So what you should imagine here is I'm going to draw a higher dimensional polytope like this as a hexagon. That's a higher dimensional polytope. Now I'm not going to draw just a triangulation of it. I'm going to allow also objects like that. Okay, so I'm going to replace the triangulation of a polygon with these sort of exotic things when you allow tripods and higher partitions.
So more of like a polygon subdivision or something?
Not higher dimensional analogs of...
Oh, yes, yeah.
Yeah. So just the point is you don't have two splits into two pieces, you allow three splits on the first residue, fourth, and so on.
In what sense do you look at the boundaries and inspect k equals 2 compatibility in this picture?
Yes, in k equals 2 compatibility, you have the structure. If you take like delta 3,6, the hypersimplex 3,6, and you take one boundary, x1 equals 1, that's equal to delta 2,5, which is which gives you a 5.5 cubed. So delta 2,5, if you take these triangulations of it, matroidal triangulations, then that gives you the 5 cubed. So that's the sense.
can you see this delta 2,5 on this picture, the one with 3 speed?
This one?
Yeah.
This is for 6 points.
I understand, but you said that we would like to understand where the crossing chords come now, right?
Yes, sorry, yes.
So this picture is somehow about generalization of chords?
Yes.
Equal to 3. I will say that there's a picture which allows you to reduce k by 1. Can I see it on this picture? Is this reduction? Yeah.
No, you cannot. I could take like, can I, let me think a minute.
I think that the question is, I mean, if I take 2 of those splits, right? And how do I know that they are compatible or not? From this picture, but using the k equal to 2 notion of compatibility.
Right. So using the k equals 2 notion. Yes. So I'm just talking about k equals 2 now, yes. The hypersimplex delta 2 4 is it's an octahedron. We're going to put like an x 1 3 on that vertex and an x 2 4 on that vertex. So what does this mean? Instead of so we have like what we have is when you put x 1 3 here, you have some tropical hyperplane that cuts through it this way, just horizontally, like this. When you put it here, it cuts through it vertically. And when you superimpose those, then you induce a full triangulation of this thing, right? I just cut it like that, and I induce a triangulation, and that's the violation of the matroid condition. So in this picture, it turns out that everything is compatible. But in order to see the incompatibility, everything reduces to the k equals 2 and n equals 4 point amplitude. It's all this picture, just many, many copies of the octahedron. Does that answer the question? Okay, so yeah. Anyway, just a quick word about linear independence. Linear independence is just a little bit of an elaborate calculation, but the main point is that there's applications of it. Let's focus on the applications of this construction. So once we actually have our xj coordinates on the kinematic space, we can actually construct a system of coordinates on our configuration space. So, and these things are kind of in duality in a pretty nice way, right? So we have xi like in the case k equals 2. We have these two kinds of coordinates. We have x 2 4 equals s1 2. And this is in duality with a certain cross ratio on M04, which is U24 equals P13, P24, P12, P34. So the point is, there's actually a duality. The planar, these xj variables, they inform like a duality between the kinematic space and the configuration space. And it's constructive, and so the idea is that you take m from mkn, and we can organize the singularities of this using this xj, these xj variables. Okay, so I want to move to, if there are any no questions, sort of more general questions or anything. I want to move to the construction of different quantum field theories. All right, so far we've had the cubic scalar. I want to move to some more exotic theories here. And for that, what we need to do, we start with our xij's. usual propagators. On the configuration space side, we have these so-called U variables. And now we have some analogous cross ratios on X and N on the configuration space. So we have our amplitude, like M24, 1 divided by X13 plus 1 divided by X24. And in the construction of Nima, Carolina, and friends, we take a deformation of this, and we find that a different amplitude, the amplitude for a different theory, lives inside. So what we're going to do is we take 1 over x13 plus delta plus 1 over x24 minus delta. We take this kinematic shift, and we're going to expand this around delta goes to infinity and extract the leading order coefficient. Okay, if we do that, it turns out that the leading order cancels. We have a negative x13 plus x24 over delta squared, and so on. And what they in their work, they said that, well, this guy is the amplitude for a different theory, for the so-called NLSM model. Okay, so why is this possible, though? This is possible exactly because this is a basis. Because the x's are independent. Right? You couldn't take a deformation of them, a generic deformation, unless the x's were independent. And that's why we needed our directed distance formula. Okay. All right, so what we're seeing is that we're going to see that the NLSM amplitude emerges from trace phi cubed, like we see in this 4-point example. And the planar basis tells you how to extend this to higher k. Makes it possible. So yeah, this planar basis, it really guides our study. Okay. Yeah. So we take the key part is we take our xj basis and we have to figure out which deformations are the right ones. Okay, so when I take this deformation, this turns out in the case k equals 2 to be the unique deformation that you can do. But yeah, when you go to higher k, there's a lot more space. Okay, so Nima, Arkani Hamid, Kao, Dong, Carolina, and Song He, they introduced this deformation and showed that the NLSM emerges. And the way to generalize this to higher k, let me explain how to do that. Okay, so here is our trace phi cubed amplitude. Take the sum over all triangulations of a polygon, take the product of the chords of 1 over xij. Well, the rule here is, the rule which they gave is the following. You take x odd goes to x odd plus delta, x even goes to x even minus delta. So that was the rule that they sort of introduced. And if you want to extend this rule to higher k, it turns out that you're counting the size of the intersection between I and j, and like every other index. And so you can sort of imagine here now what happens when you go to k equals 3. Yeah, and the exact same story happens. You have the nonlinear sigma model, and you're going to have you're going to have, again, this residual embedding property, that the nonlinear sigma model resides as a face, as a residue of this higher k amplitude. Okay? Yeah. So, and the reason this is possible, the reason we can take these deformations is because the x's are linearly independent. And yeah, and here's just the calculation I did down here. For the 4-point case, we take their deformation and extract the leading order coefficient, and this is the NLSM. Okay. Okay, so I want to summarize the structure. I'll give a more explicit example later, but I want to summarize the structure of the NLSM, the first new NLSM. Okay, this is at 6 points. We take a 6 point, which means corresponds to a configuration space of hexagons in the plane. And then we take a deformation of this. And what we find is that we get 18 terms, 18 quadratic terms, and 4 terms that are triple products. 4 terms that are triple products. So what we see is that all of those triple products are of 4-point NLSM. So each product actually looks like this guy, up to relabeling. And what's the kind of miracle that happens in this case is that if you take a so-called hard limit or soft limit, so we take some degenerations in the kinematic space, right? You run off in the kinematic space to some direction, and what you see is that the amplitude, the NLSM, just becomes identically zero. If we take this limit in this particular direction. I think we have so in k equals 2, there's one single possible deformation when k equals 2, which is given according to this rule. And it's non-trivial only when n is even. When n equals odd, when k equals 3, then it turns out to be non-trivial exactly when n is a multiple of 3. So if n is a multiple of 3 now, not a multiple of 2, then you get 2 distinct deformations. So yeah, I think I'll give those deformations now. So it turns out that the formula for the number of independent deformations, it's given by, the formula for the number of independent deformations is the following. It's number of deformations equal to the GCD of k and n minus 1. So that's sort of a theorem. And you can see when k equals 2, sanity check, k equals 2, then this is 0 when n is odd, and so on.
This is like the condition of that for there being a braid action on the glass algebra. If there is a combinator, is there any relation?
Exactly the same?
If they divide, yeah, you can define braid transformations. Some
Is
trivial.
it exactly divisible or is it GCD?
Oh, I see. Right. Oh, I see. I maybe misunderstood.
Yeah, but no, okay, we should talk though. Yeah, so, okay, so we have this going from k equals 2 to k equals 3. I wrote here the cross ratio coordinate on M04, M0M, just given by expressions like that. Let me outline how this happened. How did you get this? Well, here's how it happened. in the case k equals 2, what we do is the following. We have this so-called CHY, Kachazo-Yuan scattering potential. Which is given by S equals the sum of logs Pij Sij. Now we know that the x basis, the x variables are linearly independent, which means that we can rewrite this as log of Uij times Xij. A priori, we don't know what these Uij's are, but we have to calculate them. All right, so we start with this formula. We know that the x's are independent, so we just calculate these u's. Right, so the exact same story works at higher k, and you can construct these like I call them W variables. They're a little bit differently behaved than the U variables, but nonetheless, they possess some of the most striking properties, some of the most important properties of the duality between the x variables k equals 2 xij's and uij's. They sort of they preserve the most important features there. So we saw that the planar basis framework naturally extends, but the structure is richer. So yeah, this is the story I just explained. We extract the coefficients of the x's, and those are the new planar cross ratios. Okay. So that's the extension. Okay. Yeah. So here are just some examples. I mean, suppose I start after this lecture. Say, how do we calculate the deformation of the 6-point k equals 3 object? How do we do that? Well, we take a deformation wherein you send xijk, you deform that by a delta times nijk. And that nijk is given by this particular formula. You just take the number of copies of 1 and 4 in the set ijk and then subtract 1. That's all you need to know. Once you do this, if you have the expression for M36, you take this deformation, expand in delta, and then take that leading order coefficient, and that's your object. And yeah, so you see here we have like for W135. We have some higher order planar cross ratios, higher degree. Okay, so, right. So here's the idea. We take our deformation factor. So this is going to tell you a lot about why we actually get this GCD formula. Why does that appear? It's kind of mysterious. Well, if you take this product of the W variables, each raised to the index, the power nijk, then you get this. If you plug in the values for the W's, it simplifies to this expression. And this expression, you note, involves only the cyclically consecutive minors. Okay? So the rule is, you want to form, given all the minors of the form P12K, P23, K plus 1, and so on, you want to construct, like for any K and N, you want to construct an NLSM type deformation. You form all ratios of exactly these consecutive minors, which are defined on the configuration space. So that means that it's like, yeah, it has to be defined such that each index appears once in numerator and denominator. So that's That's the construction. And so yeah, that preserves cyclic structure, preserves residues and factorization. Just a bit about factorization. Again, in this case, we have x13 and x24. Well, this is the Feynman diagram for x24. There's a typo, that should be a 2. And if you send this internal propagator x24 to 0, it becomes a product of two 3-point amplitudes. 3-point amplitudes are just 1, but that's the general procedure. So that when can you iterate that? You can iterate that when you have the xij's are again in the, you have a collection of them such that they form the pairwise non-intersecting chords of a polygon. So we have our, if you want to go to M36, what are the residues of M36? Well, we have, in fact, we have one residue, x236 equals 0, x346 equals 0, and x135 equals 0, up the cyclic rotation. Okay, so that's the idea. And so there are actually 3 distinct kinds of residues here. Let me give you one of them. Okay, so when we have an x, I, j, j plus 1, I claim that that is an M26. That is a 6-point trace phi cubed amplitude. Take the residue of this guy where that equals 0, and where this guy is 0, we get a triple product of 4-point amplitudes. Let me sketch the picture here, because it's quite nice. So I want to identify, I want to sort of be able to look at, I want to start with a polygon, a convex polygon, and I want to sort of say, I want to see the factorization on the polygon itself. Right, just as in you can take a line configuration, points on the line, you can split this into points here and points here. Right? So what happens is that when you send x236 to 0, 1, 2, 3, 4, 5, 6, what you're doing is you're sort of bringing 2, 3 down until it's collinear with 3. So 1, 2, and 3 are collinear. And so what happens is, if I can rewrite this, 4, 5, 6. So here's the picture. 1, 2. We have our flattened hexagon, and we get like this identification between points 1 and 2 that maps to a point on the line. 2 and 3 maps to a point on the line. 1 and 3 maps to a point on the line. Yeah?
So this is in a different space, but the similar feature has also this m equals 6 amplituhedron. That's why we understand very little about it. But this factorization into 3 and like these multiple labels labeling the channel, that seems to be the same.
Yeah. Yeah, I mean, that's something we've been thinking about, yes. I mean, the connection, a little bit. Yeah, I don't think that's, if there is a connection or what it is, it's not understood yet. I don't know if you know. Yeah, but we should talk, yeah. Okay? So here is, here's the explicit identification of the triple product. All right, so look, we actually had like a 2-dimensional space of k equals 3 deformations. Right? When we look at the GCD of 3 and m, subtract 1, so GCD of 3 then, when n is a multiple of 3, we get a 3, and subtract 1, we get 2. Anyway, so we get 2 distinct degrees of freedom, and it turns out that this example I showed you before is not the only type. This example, remember, we had like 18 quadratic factors and like 4 triple products. That's not the only thing you can have. You take a different deformation direction and you get something with the triple product becomes a product of 2 NLSMs and 1 trace phi cubed. And yeah, and so also in that deformation you also get the 6 point NLSM occurring as a residue. So here's the picture. 1 NLSM, and trace phi cubed. So this is sort of like, it's a little bit like what happens for k equals 2, in the sense that I think Freddie Cacciazzo and others, what they found was, so NLSM is like a pure theory, only NLSM, but there are so-called mixings of trace phi cubed and NLSM that occur. So some particles are going to be of type trace of phi cubed, and some are going to be of type pions. Some are going to be pions. So this is kind of, we're seeing some kind of shadow, that's some kind of shadow of the phenomenon we see here. So in general, like, there's just an incredibly rich story at higher k of mixed amplitudes. So it sort of says like, whatever we see for k equals 2 for the NLSM, there's just going to be so much more to play with when we go to higher k. More deformation directions and so on. And the Adler zero, for the experts, the Adler zero has some analogs as well. Yeah, but know very little about it.
Does this factorization structure depend on the direction in the deformation space you go, or?
Yes. Yeah, I mean the type of the residue. I mean it's going to be still a product of the same types, it's still going to be a triple product. Just the types of the factors is going to be different.
Same number of terms, though.
Yes. Okay, so as an example, here's the 6 point NLSM. Right? We have six guys where the x's have the same parity. And then these 3 sort of double products in the numerator. If you take the residue of M36 and take the deformation, well, you can see already, right? You can just see it by inspection. So the structure is just exactly the same. It couldn't be nicer. It couldn't be prettier. Okay, now for like I call it a proof of life. I want to show that there's a systematic way in which the NLSM embeds into as a residue of the generalization. And for this particular thing, we took a deformation this way. N is even, k is whatever. K equals 3 here. And yeah, and so we take the intersection just like k equals 2 with 1, 3, 5 up to n minus 1. Subtract 1. That is something. It's some mixed amplitude. But then we take this particular set of residues. 2, 3n, 3, 4n, 4, 5n, and so on. That localizes this to this configuration. We take one more residue of that, and we get our n minus 2 point NLSM. So that's it's really beautiful. It's really satisfying. The identification is just simply, in this case, the identification is that the xij is equal to xijm. So it couldn't be simpler. Went the wrong way. Maybe I'll... Am I going the right direction? Oh, I had it upside down. And here we are, yes. So here's just the picture I drew, right? That's exactly the picture I drew. You localize n minus 3 points to a line, and the rest are generic. And you can see exactly that if you put the last index to n, then you get like a trivial bijection between the two. So that's, yeah, that's the story there. Maybe I'll continue. Yeah, so here is, I want to give the quadratic, the 18 quadratic guys, and the 4 triple products. And the feature here is that every hard and soft limit is identically 0. So that's an important thing. But, yeah. So an open problem is to classify when this happens. To look at this at higher 3, n for larger n, and to look at it for general k and n. That's a challenging open problem. Yeah, so...
Like to wrap up to leave.
I am, yeah. Let me skip some slides here. I think, yeah. So we've seen the planar basis, xj's. Seen that the NLSM is hidden inside trace phi cubed, we knew that. But we get this novel 3-split factorization, we get these mixed theory residues. We replaced Feynman diagrams with tropical geometry and these matroid subdivisions. And we've seen that somehow the configuration space geometry, it knows everything. It knows everything about not only like the trace phi cubed and the NLSM, but it knows more when you go to higher k. It knows a bit more, and we're trying to figure out what the extent of that knowledge is. Yeah, so summary future directions. Dimension of the space of pure kinematic shifts is GCD of k and n minus 1. You can prove that just by counting the intersection of counting the number of ways to put the frozen Plücker coordinates. The cyclically consecutive Plücker coordinates is a ratio that is torus invariant. That's a nice proof. But the open questions are, what are the higher, the k greater than 3 structures? I was able to compute like an 8-point, some 8-point in k equals 4 generalized NLSM amplitudes. And yeah, there are some tricks you can do. It's difficult, we need more ideas here. So what is the Yang-Mills, the construction of Yang-Mills, and the analog of that is in progress. Is there a gravity theory? There's some notion of that. And all of this we're doing at just QFT amplitudes. Can we extend this to string theory? And I think that's it. Thanks a lot.
So we can start the discussion here.
There are natural generalizations of the CEGM amplitudes. So the tropicograph-Mannion is constructed with the Plückers, but you can take the parity invariant subset of those or the parity completion of those and write versions of the tropicograph-Mannion and write amplitudes. So do you expect them to factorize in this in the formations as well?
Yes, I think, and I needed to do that. I had to, so take the G36 case.
Yeah.
Starting there, I actually needed in one, so it's a little bit subtle. I'm going to say two things. I was constructing doing the Yang-Mills amplitude. So I started with the 3/6 case. I took this deformation, a different deformation we've discussed today, and the object was just a mess. It's a complete mess of x's, just a big polynomial. But it turned out when I included the additional cluster variables, It was no longer a mess. It got rid of the there were linear dependencies among the expression, which the cluster variables clarified. So yeah, it's probably going to be a good thing to look at.
So can we see examples of this 3-6 compatibility? So can you, off the top of your head, if not, that's okay, write two triangulation, not triangulation, generalization of triangulations in this hexagon, let's say this that you drew, that are not compatible, and how we can see pictorially that they are not compatible by looking at these boundaries that you mentioned and analyzing k equals 2.
Let's see. Let me think for 2 seconds. I mean, so on the one hand we have triangulations of polygons, but you can take Plabat graphs too. All right, so the k equals 2 Plabat graphs are like exactly triangulations of polygons. They're exactly like related to them, equivalent. But if you want to find the x's, you want to find Feynman diagrams and only the xijk's, then you want to write down all Plabat graphs, all maximal Plabat graphs there. And so the condition that says when two xij's go in the same Feynman diagram, well, that's exactly when can they fit together in a Plabat graph. Okay, you asked about the configuration space. And the answer is, my answer would be that you have to go to a delta 3-6, right? And you have to zoom in on one three-dimensional boundary. And you just look at when do you have a octahedron that is fully triangulated? Because in that case, if you have a fully triangulated octahedron, that is not an accessible point from the configuration space. It's because the configuration space basically corresponds to polytopes that have edges only in the root directions. You can't join opposite things.
Can you clarify the point about the independence of these x variables now? I'm slightly confused. So if you have x, I plus 1j, this reduces to the k equals 2.
No, it just looks like it. Yeah, it's actually, so the Mandelstam invariants here are like Mandelstam tensors. Right? So it looks like, I mean, if we have like x, let's say x 3, 4, 6, n equals 6. That's equivalent to S1, 2, 3 plus S1, 2, 4 plus S1, 3, 4 plus S2, 3, 4. Okay, these are coordinates on a much bigger kinematic space. These are not like not linear combinations of Sij.
So there is no limit to k equals 2.
There is. It's just there's something that happens beforehand, in which case all of these are linearly independent. The limit to k equals 2 is the following. We take an xijk, take an Sijk, and we sum k equals 1 to m. And that's an Sij. This satisfies steady momentum conservation.
Okay, but this doesn't impose in the end some relation between x's?
No.
Because the Sij's do satisfy relations.
Yes.
So they become trivialized at the level of x's, or relations between Sij's?
You don't have any sums of this type in there. I mean, it's sort of orthogonal. I don't want to say it's orthogonal to it, but yeah, this has no consequence for the x's. So the kinematic space here is like n choose 3 minus n. And it just happens, it's like there exists a projection of this space onto the k equals 2 kinematic space. That's to say then. Yeah, and in this projection, like the, oh yeah. Yeah, so there is a projection there.
So the minus n is for 3 adjacent, or
Say again?
sorry, can you repeat again why there is minus n? Why is it not just n choose 3?
Oh yeah, because it's cyclically adjacent, guys. Yes, that's like this for the x's. That's what it is. The cyclically adjacent, like x1, 2, 3 equals 0.
Okay, so
But this is also j equals 4 to n of sorry. It is the sum ij equals 2 to n of s 1 ij. So we have these n linear relations. Replace 1 with any 1 through n. That's statement is that's equivalent to imposing that x1, 2, 3, and so on is equal to 0. I mean, lest you think this is like an arbitrary thing, I mean, having this dimension, this momentum conservation, this is what gives you this duality. This is what gives you the duality between m kn and m minus k n. That's what gives you the Grassmannian duality.
I have another question. Early on one of your first slides, you mentioned in the tools that you use in this paper with Cachasso from 22 mirrors to the potential construction.
Yes.
But I didn't see it pop up.
Right.
Could you comment on that and how it comes in?
Yeah. So that's a beautiful story. If we take what happens is the following. We take. Let me use, to be concrete, we take n equals, okay. We specialize this to xijk equals 1 for all ijk, non-cyclic. Well, this is equal to the number 42. 42 is the number of the number of 3 by 3 Young tableau. It is also, how to say this quickly, it is also the volume of a certain polytope. And that polytope is dual to this mirror superpotential. So if you take the mirror superpotential and take its Newton polytope, that Newton polytope is related to the volume, this 42 here. So, yeah, I guess that's in a short amount of time, that's about the best they can do.
Are there any more questions? Okay. If not, let's thank Mikkel.